So this is a convenient unit it's called the diopter. Its units are 1 over m. So 1 over meters is the unit of diopters. And what it tells you is the converging, it can also express diverging power of a lens. So how hard does this lens work to bend rays and in which direction? So if I have parallel rays coming in and I have, let's say, a really thin lens here that's so thin that I'm not going to draw it, and then these rays converge to some point here. And that's supposed to meet. Let's suppose this distance, just as a simple example, let me write 20 centimeters. Right. So the focal length is 20 centimeters. The diopter is just going to be the inverse of that. So it's just 1 over f. So in this simple example, we would have a 5 diopter lens, which we write as 5 capital D. So this is a 5 diopter lens, 5 diopter lens. So in general we write 1 over focal length D diopter. So you can think of it as you know, if I were to perform this operation over and over again, I took parallel rays, converge them to a point, and then start with parallel rays again and converge them to a point. This tells me how many times in a row I could keep converging parallel rays inside of a meter, right? One way to look at it. I don't know if that's helpful or not. I find it helpful. So it gives me, you know, the higher this number is, the more times I could converge parallel rays in a small amount of space inside of 1 meter, let's say, right? And if this is less than 1, what does that mean? If it's between 0 and 1, let's say, yeah, between 0 and 1, not including 0, what would that mean? It's going to take more than a meter to converge those rays. So they may eventually converge, but it'll take a while. And if it's equal to 0, what does it mean? So the lens should look like a flat piece of glass that just keeps the rays all, the parallel rays all go through and continue on their merry way without being affected, right? If we have the case of a diverging lens, so for a diverging lens we get negative 1 over f diopters. So you can just write a negative number, and so that will correspond to the amount of divergence. And if you remember this picture here, so I guess in this case the focal point would be written as this f here is written as a positive number, and then you make it negative there for diopter. We could have instead made this a signed number and said f is negative for diverging lenses. It's just a convention. And so as you see, the stronger the divergent power of this lens, the closer the focal point will be to the center of the lens, correct? To the central axis of the lens here. So and so that makes good sense, right? So if you had a diverging lens of negative 100 diopters, where would this focal point be? Be like 1 centimeter away, I think, from the left side of the lens, right? Assuming this thing has 0 thickness and doesn't get in the way of the lens itself. Right? Okay. So there's one very nice property about using diopters, and this is why optometrists prefer to use it. Those of you who have prescription glasses may have heard a lot of discussion about diopters and such in correcting your vision. And what's nice is that in combining lenses or interfaces, I'll say interfaces between media, the overall power is D equals D1 plus D2 plus d3 plus dot dot dot. So you just take the diopter of your lenses that are all together sequentially in a system and just add them up. So that makes the algebra very simple. So an optometrist doesn't have to pull out a calculator, do some very complicated calculations in algebra and all these kinds of things, right, by calculating 1 over and then adding and then pulling it 1 over again. So using diopters just makes it very easy to reason about the power of a sequence of lenses that are arranged in space, and it will work even if they're combining converging and diverging lenses. So I think that's very nice, right. So once you've done this 1 over f conversion or minus 1 over f conversion in the diverging case, then you just add up these d values and it ends up being very nice. Questions about that? Let me talk a little bit about the structure of the human eye, and I will tell you what the diopter of the human eye is. Anybody know the diopter of the human eye? Anybody want to guess? 40? Pretty good, right? So the diameter of the eyeball is around 20 millimeters. So that means the focal length should be around that roughly. And if the focal length is around that, then maybe some ballpark estimate would be 1 over the focal length, which would be about 50, right? Isn't that interesting, right? Because you have parallel light rays coming in, let's say, and you have to focus them on the retina. So let's look at this picture. Kind of hoping this one would be looking to the side like our eyes normally do, but this is an eyeball looking straight up. So, so the light's coming in from the top. The rays of light pass into the cornea. Then there's this liquid area here. You may feel sometimes like your eyes are dried out, especially if you're dehydrated. So the aqueous humor corresponds to a liquid area where the liquid's very frequently refreshed for cleaning purposes, let's say. In through your pupil the light goes. You have a lens which is called the lens. This lens is controllable, so you have muscles that can squeeze this lens or contract the lens, and that will change its diopter, and then that will change the diopter of the entire system. If you're older, this happens roughly in people's late 40s on average, then the ability to change the shape of this lens will start to deteriorate, which is why older people have reading glasses. And so you have automatic high-powered reading glasses built into your eyes if you're young, and eventually you'll lose that. So sorry, that's the way it works. So the light comes in and then it eventually hits the retina. It has to travel through this other liquid here called the vitreous humor. There's nothing funny about it, but it's humorous, the kind of liquid, I think, in Latin. And it hits the retina. Notice how the retina is curved all the way around like this. So that's different from projection screens or camera imaging systems that we tend to make, because things in engineering, I said this before, in engineering we tend to like rectangles and flat surfaces and things like that. I know people are getting wild with curved screens now, and you know, in the industry, and so they're trying to break out of the mold. But just notice that the images that are projected onto our retina are actually being projected onto a curved screen, but it's okay. The entire optical system is designed for that. And the part of greatest concentration where we can receive the most information in the highest density is at the fovea. Because of that, we end up rotating our eyes very frequently. There's some other reasons why we rotate our eyes, and I'm going to get into these kinds of details, but I just wanted to point out that while I'm talking about focal lengths and focal planes, and I will be talking about images forming, keep in mind that your eye is an optical system. Now let me say a couple of things about its optical power, and then I will talk a bit about image formation, probably after the break. So if we look at this top part, again, we have light coming in through the cornea, travels through this aqueous humor, goes through this hole, which is the pupil, then traverses the lens, then traverses the vitreous humor. So it looks like there are 5 different materials that are relevant here. Let me try to draw a picture of that a little bit. So we have the cornea. We have out here air, assuming you're not swimming underwater while we're talking about this, which will of course affect your vision. Then we have the aqueous, Then we have, there's the pupil where the light comes in, and then there's a lens on the back side here. So this is the lens. So the rays of light that are coming in, I'm pretty sure I can't draw all the bendings correctly here. Comes in like that, let's say, right? And eventually has to go back and hit, I guess I've drawn an enormous eyeball here, so it has to hit the retina back here somewhere, right? So let's look at the refractive indices of these various materials. So there's air out here, which I'll call N1. I'll have N2 for the cornea. I'll have N3 in the aqueous. I'll have N4 for the lens, and I'll have N5 for the vitreous, which is it's also a kind of liquid or more like gelatinous, let's say, material. So what's interesting as well is that once the light hits the cornea, it never really sees air again, right? It goes through all this liquid gelatinous stuff and then ends up on your retina, which I find kind of interesting, right? So it's not like the optical systems that we build in engineering. So here are the refractive indices. Air is well, about 1. When I looked up these numbers, it was 1.009. I'm sure it depends on things like altitude and humidity and other things, but I'm no expert on that. 2, the cornea is 1.376, and 3, the aqueous or ocular fluid is 1.336, so not too different. So there's not too much of a change going from the cornea to the aqueous. N4 lens 1.4, so a little more significant change there. And then vitreous is similar to the aqueous, so N5 is 1.337. Okay, who knows what the precision is here? That's essentially the same, I think. So air, cornea, aqueous, lens, and vitreous. Notice where the biggest transition occurs. Where's that at? So air to cornea. So actually the optical power, the convergence power that's greatest in your optical system is at the cornea. So your cornea is doing more work to bend light than any of the rest of these, including the lens, which I find quite amazing. So that surprises me, and I remember emphasizing this over and over again to my students before in teaching this class, and they still get it wrong on the test every time. So be careful. The cornea is the place where the greatest bending power happens, the greatest amount of refraction happens in the eye's optical system. So if you combine all of these, if you go through and do the math, which I'm not doing here, the total power of the eye's optical system is 59.52 diopters, which corresponds to a focal length of 16.8 millimeters. Right, so that's quite a powerful lens. When you combine it all together, that's quite a powerful lens, right? It has to severely bend the rays. If I just go and buy some lenses online somewhere, you know, which I have a set of lenses here if you want to play during the break, by the way. If you just go buy some standard lenses, chances are they're not so highly curved as to achieve nearly 60 diopters, right? So the optical system that we have in our eyes is very, very powerful. Any questions?